This is Chem 207 major revision. So I would go through what you need to know in these experiments. So we started with test for alcohols. Let's test for alcohols. And there are three methods used in the test for alcohols. The first one was the Ester chloride test. Ester chloride test. Ester chloride that CH3 H3 is Ester chloride. It has a chlorine, as you can see over here. Is Ester chloride. So we have the Ester chloride test. Then we have the Lucas test. We have the Lucas, where we made use of the Lucas reagent. Lucas reagent is zinc chloride in HCl. That's dissolving HCl. That makes up the Lucas reagent. Then we also have the chromic acid test. Chromic acid test, right? Or we call it the Jones oxidation test. Jones, right? So these are the basic tests used in the test for alcohols, right? So basically we'll start with not wasting much time, start with the Ester chloride test. You need to know that the Ester chloride test is basically used to confirm that a compound is an alcohol. So Ester chloride test does not tell you if it is primary, secondary, or tertiary, right? It does not tell you. It only tells you that that compound contains the OH group. So that is what the Ester chloride does, right? It can only tell you that a compound contains an OH group. So, and it does this by the evolution of heat and hydrochloric acid. So the evolution of these two tells you that that compound or that sample to be tested contains an OH group, and that's only made possible with the Ester chloride. I've shown you guys the structure earlier on, so, and that is basic for that. And then we have the Lucas test, where we made use of the Lucas reagent. The Lucas reagent is zinc chloride and HCl. So all you need to know, what is it used for? The Lucas test. What is it used for? Primarily, it's used for differentiating between primary, secondary, and tertiary. It does differentiate them. It's used for differentiation of alcohols, primary, secondary, and tertiary. Okay. While primary alcohols, they don't react. They do not react at room temperature. They do not react easily at room temperature. So the tertiary alcohol reacts slowly. They are slow. All right. Why the secondary, why the tertiary, right? Why the tertiary reacts very fast. So with that being said, and their reactivity is based on what we term as the formation of a carbocation, right? Let's start with this. right? The tertiary carbocation is more stable than the primary carbocation, while the primary is more stable than the while the secondary, this is secondary, this is primary, this is tertiary. So it depends on the stability of the carbonium ion formed, right? That tells you the rate at which they all react with the Lucas reagent. I would talk more on this in the next test, that is the chromic acid test. So in the chromic acid test, I just said earlier that chromic acid test is also known as the Jones, Jones oxidation test. Okay, let me reduce this a bit. So it's also known as the Jones oxidation test. Don't forget that. So basically, the Jones oxidation tests, as we've rightly implied or said, can only be used to differentiate between. So it's used in differentiating between primary and secondary alcohols, that's OH. They are used in differentiating between primary and secondary alcohols from tertiary alcohols, right? So that's to tell you that these two can react similarly with chromic acid tests, with the chromic acid reagent. Okay, so whereas tertiary does not react, so the tertiary alcohols does not react, while the primary and secondary alcohols do react. Now chromic acid test is Jones oxidation. It's an oxidation process. So the primary alcohols are usually oxidized to aldehydes. The secondary are oxidized to ketones, while the tertiary does not get oxidized. Now, why is this so? You have to know the reason to everything that is being told to you. You must know the reason why these things are this way. You don't just take it up like that. So I'll make use of an example. If we have, let's draw this compound, right? Let's say this is CH3, this is an OH, then here is H3C, right? If you look closely, we have this. Let's draw another one, H3C, C, then CH3. Let's have an OH here, then we have hydrogen here. Okay, now let's draw the third one. We have CH3, we have C, we have H, we have H here. Let's say we have OH. Now you can see this is 1, this is 2, this is 3. Now let's start with the first one. The first one you see here. Now what kind of alcohol is this? This alcohol is the tertiary alcohol. This is tertiary alcohol. Why? Because it contains 3 alkyl groups, 1, 2, and 3. It's a tertiary alcohol, right? So if you look closely in the structure of tertiary alcohol, there's no hydrogen. Now let's go to the next one, which is this one. This contains 1 alkyl group here, another alkyl group here, no other alkyl group. What you see here is hydrogen. It is not an alkyl group. Okay, so secondary alcohols contain, this is secondary, 2 alkyl groups. You can see it has 2. Tertiary has 3, right? Now let's go to the next one, which is the structure. This one contains only 1. It has 2 replaceable hydrogens. This one has 1 replaceable hydrogens. Now primary, this is primary, and secondary can react with chromic acid test or chromic acid reagent, can react with chromic acid, so to say, to give you aldehyde and ketones. So the primary alcohol gets oxidized by the chromic acid reagent to give you an aldehyde. Secondary gets oxidized to ketones. Now tertiary, which is this one, does not get oxidized because it does not contain hydrogen that is found in the primary and secondary. As you can see, there's no hydrogen here. There's no hydrogen in the tertiary, no replaceable hydrogens if you check. So this is the major reason why. Okay, so and let's go to the next experiment. Experiment 2. Experiment 2 had to do with preparation of ethene gas by dehydration of an alcohol. Precisely, ethanol was used. Ethanol was used to produce ethene gas. You just have to know the basics and the theoretical aspect of it. So basically, you should know how ethene gas was collected. Ethene gas, which is being produced from, let's say, ethanol. This is ethanol in the presence of an acid with some heat, gave you ethene, C2H4. All right, so ethene gas is less dense. All right, it is less dense, meaning that it is less heavier. Less dense, meaning that, sorry, this is dense, meaning that it is less heavier than water, and that is why it is collected by downward displacement. It is collected by downward displacement over water. If this is water, ethene gas will be residing here. All right, and we collect it by downward displacement. Don't forget, it is less dense and it's less heavier. So that is basically it. Let's go to, and you should know how to show the equation of reaction, of course, for the chemical reaction between ethanol and sulfuric acid. Okay, now let's go to the third one. The third experiment. The third experiment basically had to do with the preparation of phenyl benzoate. Phenyl benzoate using method Scotton-Bowman's method. Okay, that's a method used in production of phenyl benzoate, and phenyl benzoate looks like, oh sorry, the phenyl benzoate looks like this. This is phenyl group. This is basically phenyl group. So we have C double bond O, then O C6H5. So we basically could have 1, 2, or let me just shortcut that. 6H5. Okay, this is basically phenyl benzoate. Right, so it's produced through the Scott-Bowman's method. You should know the reagents and the equation of reaction, right? And basically we use this reagent. Sodium hydroxide was used, right? It's a nucleophilic process of reaction. Sodium hydroxide was used in the preparation of the phenyl benzoate to facilitate the process by converting the phenol, this is phenol, into an efficient nucleophile. We wouldn't go into the reaction mechanism. So sodium hydroxide helps in converting the phenol into an efficient nucleophile, meaning electron rich, that would help in the formation of the phenyl benzoate. Okay, you are asked to determine the melting point. No one is going to ask you melting point of phenyl benzoate. No, you should know the chemistry, right? So in the next experiment, that's the fourth experiment, the preparation of derivative of aldehyde and ketones. There you made use of what is called Brady, B-R-A-D-Y, Brady's reagent. A mistake in your manual read brandy. No, it is not brandy. Okay, it is Brady's reagent. So Brady's reagent is 2,4-dinitrophenylhydrazine. So that is basically Brady's reagent. Okay, so the carbonyl group is what is responsible in the formation of what we call 2,4-dinitrophenylhydrazone. When 2,4-dinitrophenylhydrazine reacts with a carbonyl group found in aldehyde or ketones, a 2,4-dinitrophenylhydrazone is formed, which is usually yellow or reddish. It's usually yellow or reddish. Okay, so that is the derivative of an aldehyde or ketone is 2,4-dinitrophenylhydrazone. For clarity, and we will not be going to the reaction mechanism. If you check this video description, you see a mechanism on that. So 2 4 sorry, this is a comma, 2,4-dinitrophenylhydrazone zone is the derivative of an aldehyde or a ketone, and you know the carbonyl group is responsible for the reactivity of the aldehyde RCHO or the ketone RCOR. This is a ketone, right? So you should know that. And the process, the reaction is typically nucleophilic elimination reaction. Okay, so that's by the way with that experiment. So in the last experiment that had to do with separation of components of a mixture using TLC, okay, using TLC, that's thin layer chromatography, right? You need to know what the method of separation is used for precisely. It is used for separating components of a mixture, not compound. Right, it is not compound but a mixture, right? So the TLC plates, something like this, okay, coated with silica. Yeah, the white surface is silica and it constitutes what is called the stationary phase. Stationary phase made of silica, SiLiCa, okay, while the mobile phase is suitable solvents. You know, you put it in the beaker or a system. All right, and the mobile phase, which I said is made up of solvents, typically N-hexane, ethyl acetate usually can be used as a solvent. Okay, and the affinity of the component of the mixture to the stationary and mobile phase constitute what we know as a detection factor. Distance moved by the mixture sample component, distance moved by the sample component over distance moved by the solvent. So you already know this formula, so you should know how to substitute and make use of this formula. And in a case probably you are given retention factor, you could be asked to find the distance moved by the component of the sample, or you could be asked to find the distance moved by the solvent itself. All right, since you already know that retention factor is distance moved by components of sample over distance moved by the solvent. So if you know this and you know this, you can get this. All right, vice versa. All right, anyone can be given. Okay, so and you should also be able to interpret something that looks like this. If you have let's say distance moved by solvent, this, then let's say here's 10, right, and here's 5. Okay, can just come in different ways. So if this is a retention factor, distance moved by the component of the sample, you can see it's 5 centimeter here, so it's going to be 5 over distance moved by the solvent. All right, here's 10. Whatever it gives you is the retention factor. It doesn't have a unit, it's a factor. Okay, so you don't have to put a unit. So this is typically what I expect you all to know, and good luck.